The images dropped 48 hours ago. No press conference, no countdown, just raw data uploaded to NASA's public servers from multiple spacecraft positioned across the solar system. Mars Reconnaissance Orbiter, MAVEN, Stereo, SOHO, all trained on the same target, 3I Atlas, and what they captured wasn't supposed to be possible. The coma brightened again after weeks of predicted decline. The tail reshaped itself in ways that thermal models said couldn't happen at that distance. And deep inside the nucleus, temperature readings revealed activity that no one forecast. These are the clearest images of an interstellar comet humanity has ever seen. Not artist renderings, not simulations, actual photographs showing a visitor from beyond behaving in ways that challenge everything we thought we understood about how these objects work. This isn't speculation anymore. This is data, fresh, verified, unsettling. What would you do if you were the scientists who opened these files first? 3I Atlas entered our detection range in late 2024. It came from the constellation Ursa Major, moving at 54 kilometers per second on a trajectory that proved it originated outside our solar system. The initial observations suggested a dormant object, dark, silent, a frozen fragment that had been traveling through interstellar space for possibly millions of years. But as it approached perihelion in March of 2025, something shifted. A faint glow appeared around the nucleus. Scientists called it a coma, the cloud of vaporized gas that forms when solar heat reaches subsurface volatiles. Then came the jets, asymmetrical plumes, erupting from specific locations rather than the entire surface. And finally, a tail stretched millions of kilometers behind the nucleus, scattering sunlight in patterns that didn't match standard cometary models. The astronomy community watched closely. Some predicted the activity would peak at closest approach and then fade as 3I Atlas moved away from solar heating. Standard physics, predictable behavior. They were wrong. In late April, weeks after perihelion, the new images revealed something unexpected. The coma hadn't dimmed. It had brightened. The tail hadn't dispersed. It had restructured itself, developing density variations that shouldn't exist at that distance. And thermal readings from Mars orbit showed temperature spikes in regions that should have already cooled. This wasn't following the script. Every comet we've studied from our own solar system obeys a relatively predictable pattern. Heat input correlates with outgassing. Distance from our star determines activity levels. The further away, the colder it gets, the quieter it becomes. 3I Atlas was defying this pattern in real time. The images showed jets that pulsed rather than flowed steadily. Tail sections that maintain coherence over millions of kilometers despite radiation pressure that should scatter them. Color shifts near the nucleus that indicated fresh ice exposure, as if internal layers were collapsing and revealing material that had been shielded for eons. And the timing made no sense. Why would activity increase after perihelion? What internal structure could explain heat penetrating deeper into the nucleus weeks after peak solar flux? The data was verified. Multiple spacecraft, multiple wavelengths, independent observations, all confirming the same thing. 3I Atlas was behaving unlike any comet we had detailed records for. Comment what you think is happening, even one word. By early May, NASA had compiled the most comprehensive data set ever assembled for an interstellar object: infrared thermal maps, ultraviolet emission spectra, visible light photography, stereoscopic three-dimensional modeling from Stereo's dual vantage points, and continuous monitoring from SOHO as the comet's tail swept through Earth's orbital plane. This wasn't a glimpse. This was sustained observation across multiple platforms, capturing an object from another star system as it responded to our star's energy in ways that didn't fit our existing models. The scientific community began asking uncomfortable questions, not about whether the data was real, that was confirmed, but about what it meant, about whether our understanding of cometary physics was complete enough to explain an object that formed in a different stellar environment, under different chemical conditions, with a different thermal history. 3I Atlas was a test case, and we weren't sure we had the right equations. The Mars Reconnaissance Orbiter provided the first breakthrough. Its infrared camera captured thermal maps showing temperature variations across the nucleus that changed on timescales of hours, not days. The sunward hemisphere would heat, then cool rapidly, then reheat in localized patches. This suggested subsurface venting, material erupting from below, collapsing cavities, and fresh surfaces being exposed continuously. Normal comets show gradual thermal changes. 3I Atlas showed rapid fluctuations that indicated structural instability. MAVEN, positioned to study Mars's upper atmosphere, turned its instruments toward the comet and detected ultraviolet emissions consistent with water vapor, carbon dioxide, and trace organics. The ratios were close to solar system comets, but slightly offset, as if the chemical composition reflected formation conditions in a molecular cloud with a different elemental mix than our own. The stereo spacecraft, separated by millions of kilometers on opposite sides of our star, provided stereoscopic imaging that revealed the tail's three-dimensional structure. What looked like a smooth stream in 2 dimensions turned out to be a complex braid of filaments. Some sections were denser than others. Some had gaps. The particle distribution suggested that outgassing wasn't constant but episodic, releasing material in bursts rather than steady flow. And SOHO, the Solar Observatory, captured the moment when the tail brightened again 2 weeks after perihelion. This was the anomaly that caught everyone's attention. Standard cometary behavior predicts peak activity at closest solar approach, followed by gradual decline as the object moves away and cools. 3I Atlas followed this pattern initially. Activity peaked in late March, then began to fade. But in mid-April, the tail suddenly brightened again, achieving nearly the same luminosity as perihelion, despite being significantly further from solar heating. The data forced scientists to reconsider their thermal models. One hypothesis suggested that heat was penetrating deeper into the nucleus than expected, reaching volatile pockets buried beneath an insulating crust. As surface layers eroded, these pockets were exposed, triggering delayed outbursts. Plausible, but it required the nucleus to have a very specific internal structure that we couldn't directly observe. Another hypothesis proposed that 3I Atlas was a rubble pile, loosely bound fragments held together by weak gravity with voids between chunks where volatiles accumulated. As the object rotated and different regions faced solar heating, these voids released trapped gas in irregular patterns. Also plausible, but again, unverifiable without direct sampling. A third hypothesis focused on the comet's rotation. If 3I Atlas was tumbling rather than spinning smoothly, different surface areas would receive varying amounts of solar energy over time, creating activity cycles that didn't align with simple distance-based predictions. Possible, but rotational data remained incomplete. None of these explanations were wrong. None were proven. The images provided unprecedented detail, but they also revealed how much we still didn't understand about objects that spent millions of years in conditions we can't replicate or directly study. The color shifts added another layer of mystery. Early images showed a neutral gray coma, Later observations revealed a blue tint near the nucleus, fading to brownish tones at the tail's outer edges. Blue light scattering indicated freshwater ice with small particle sizes. Brown indicated older dust coated with organic residues. The transition between these colors suggested ongoing erosion, with fresh material continuously being exposed as surface layers ablated away. But spectroscopic analysis revealed absorption features that didn't perfectly match any compound in our reference databases. They were close: water ice with impurities, carbon dioxide mixed with silicates. But the exact spectral fingerprint remained unidentified. Maybe it was an isotopic ratio uncommon in our solar system. Maybe it was a mineral combination we don't see in local comets. Maybe it was contamination from the interstellar medium during the comet's long journey. Maybe is where science gets uncomfortable. Every measurement raised questions that required more data to answer, data that was becoming harder to obtain as 3I Atlas accelerated away on its hyperbolic escape trajectory. A equals natural phenomenon following known physics. B equals natural phenomenon requiring updated models. C equals something we don't have a framework for yet. Comment A, B, or C. No wrong answers. Let's be direct about what the images confirm. 3I Atlas looks like a comet. It has a nucleus surrounded by a coma. It has jets. It has a tail. Its thermal signature matches sublimating volatiles. Its spectral features indicate water, carbon dioxide, and organic compounds. Every visual and measurable characteristic aligns with natural cometary activity. NASA scientists explicitly stated that there are no signs of artificial structure, no metallic surfaces, no geometric symmetry, no reflective patterns that would suggest technology. The object behaves exactly as expected for a comet responding to solar heating. So why are researchers still uncomfortable? The first issue is survival. Interstellar space is hostile. Cosmic rays bombard anything traveling between stars. Over millions of years, this radiation should convert surface ices into complex tars and refractory materials that don't sublimate easily. Yet 3I Atlas released water vapor and carbon dioxide as if its ices were relatively pristine. How did it shield volatile material during such a long journey? Some scientists propose that the comet was large enough that radiation only affected the outer layers, leaving subsurface ices intact. Others suggest that the interstellar medium is colder and less damaging than models predict. Both explanations work mathematically, neither feels completely satisfying. The second issue is timing. The activity spikes don't correlate cleanly with solar distance. Yes, the comet was active near perihelion, but the resurgence of brightness weeks later, at a distance where solar flux should be significantly weaker, suggests that internal heat transfer is more complex than standard thermal diffusion models account for. Maybe the nucleus has low thermal conductivity, causing delayed heating of deep layers. Maybe there are exothermic chemical reactions occurring as previously separated compounds mix during structural collapse. Maybe rotational dynamics are creating hotspots that don't align with simple sun-facing geometry. All plausible, all speculative. The third issue is the tail structure. The stereoscopic images from stereo revealed particle densities in certain tail sections that appear higher than radiation pressure and solar wind dynamics should allow. Gas and dust ejected from a comet disperse predictably based on particle size and charge. But some regions of the 3I Atlas tail maintain coherence over millions of kilometers. Scientists propose magnetic field interactions, electrostatic binding between charged grains, complex plasma effects in the coma that slow particle dispersion. These mechanisms exist. We've observed them in solar system comets, but the degree of coherence in 3I Atlas seems stronger than typical. And then there's the spectroscopic puzzle, the unidentified absorption features. They're not dramatic, they're subtle, close to known compounds, but not exact matches. This could be explained by unfamiliar isotopic ratios, or unusual mineral inclusions, or organic molecules with slightly different structures than we commonly see in our region of the galaxy. But subtle anomalies are often the most important. They're the signals that something about our assumptions doesn't quite fit reality. No one is claiming 3I Atlas is artificial. The evidence overwhelmingly supports a natural origin. But natural doesn't mean simple, and it doesn't mean we fully understand what we're looking at. The comet formed in a molecular cloud we will never observe, around a star we cannot identify, under chemical and thermal conditions that may differ from our solar system's history. It traveled through interstellar space for timescales we can barely comprehend, and now is passing through our neighborhood, responding to our star's heat in ways that challenge the edges of our models. The discomfort isn't about aliens, it's about the limits of our knowledge. It's about realizing that even when we have the best images ever captured of an interstellar object, we still can't answer basic questions about how it retained volatiles, why its activity curve looks unusual, and what its chemistry tells us about planetary formation in other systems. Does this change how you see our place in the universe? Take a step back from the data for a moment. Think about what's actually happening here. An object that formed light years away in a system we will never visit traveled through the darkness between stars for an incomprehensible span of time, entered our solar system at exactly the right angle and speed to pass through our planetary neighborhood, and arrived during the brief window of human history when we have spacecraft positioned to observe it. The probability of this sequence of events is staggeringly low. Yet, here we are, looking at photographs of something that carries chemical information from another corner of the galaxy, measuring its temperature, tracking its trajectory, analyzing its spectrum, trying to decode what its structure and behavior tell us about places we cannot reach. This is the best resolved interstellar comet humanity has ever studied. Not just observed, studied with multiple instruments from multiple angles across multiple wavelengths for an extended period. We're not just witnessing a visitor pass through, we're documenting its properties in unprecedented detail. And what we're learning is humbling. For centuries, astronomy was a study of patterns, objects that moved predictably, cycles that repeated, a cosmos that seemed, once you understood the math, fundamentally knowable. We built theories that worked, models that predicted, frameworks that made sense of what we observed. 3I Atlas fits those frameworks mostly, but not entirely. And the parts that don't fit are reminders that our frameworks were built using examples from one planetary system, one star, one set of formation conditions. When we extend our observations to objects from other systems, we discover that nature is more varied than our local samples suggested. Chemical ratios differ. Thermal properties don't match exactly. Activity curves show unexpected features. This isn't failure, it's growth. Science advances by finding the edges of what our models can explain, and then refining those models to encompass a broader range of observations. But it also reveals something deeper about the human condition. We are a species that builds understanding incrementally. We observe, we measure, we compare, we theorize, we test. Each generation adds to the accumulated knowledge, expanding the boundaries of what we can explain. But the universe is under no obligation to conform to our pace. It operates on time scales that dwarf human civilization. It produces phenomena we might glimpse once per lifetime, if we're lucky. 3. I-Atlas will not wait for us to perfect our theories. It's already leaving, already accelerating back toward interstellar space, already becoming harder to observe as distance increases and sunlight weakens. In a few years, it will be beyond the reach of even our most powerful telescopes. The images we have now will become historical artifacts. The data we've collected will be studied for decades, but no new observations will be added. This moment, right now, is the only chance we get, and maybe that's the most profound lesson. The universe doesn't grant second chances. It presents opportunities briefly and then moves on. We either capture the data while we can, or we lose it forever. 3. I-Atlas is teaching us about more than cometary physics. It's teaching us about impermanence, about the rarity of opportunities, about the importance of being ready when something unexpected appears. How many other interstellar objects have passed through our solar system without being detected? How many will pass in the future before we have better instruments to find them? How much are we missing simply because we're not looking in the right places at the right times? These questions don't have comfortable answers. They remind us that knowledge is fragile, that discovery requires not just capability, but also timing, that the cosmos is full of wonders we might never see, not because they don't exist, but because we're not positioned to observe them. Write one sentence. This means 3I Atlas is leaving our solar system. The orbital calculations are definitive. Its trajectory is strongly hyperbolic, with an eccentricity well above 1. It's not bound to our star. It came from interstellar space, passed through our neighborhood, and is now accelerating back into the darkness between stars. By the end of 2025, it will cross Jupiter's orbit. By 2026, it will pass Neptune. By 2030, it will exit the Kuiper Belt. And then, for thousands of years, it will travel through the outer reaches, gradually fading from view until even our largest telescopes can no longer detect it. Eventually, it will disappear completely. Another object swallowed by the vastness of the galaxy. NASA is evaluating whether a rapid intercept mission is feasible. The technology exists. Small, fast spacecraft could potentially rendezvous with 3I Atlas within the next few years if launched soon. The European Space Agency has conducted preliminary studies. Other space agencies have expressed interest, but the window is narrow. Every month that passes, the comet moves further away, requiring more fuel and more time to reach. The engineering challenges are significant. The cost is substantial, and there's no guarantee that a mission would arrive in time to observe the comet before it becomes too distant to study effectively. If no mission launches, 3I Atlas will become another entry in our catalog, a collection of images, spectroscopic data, thermal maps, trajectory calculations, a memory of the spring when something from beyond came close enough to photograph. But even without a dedicated mission, the data already collected will occupy researchers for years. Teams are working to refine cometary thermal models to account for delayed outgassing. Others are analyzing the tail structure to better understand particle dynamics in low-density environments. Still others are comparing 3I Atlas to Oumuamua and 2I Borisov, searching for patterns that might reveal how common these visitors are and what their properties tell us about the galaxy at large. And beneath all this analysis, a deeper question lingers. What if interstellar objects are more common than we realize, and we simply lack the detection capability to find them regularly? What if 3I Atlas is typical, and our models are tuned too specifically to solar system comets? What if the chemistry we're seeing is normal for its origin region, and the anomalies we detect are just signs that we need to expand our reference database. Science requires repeatability. One observation is interesting. 2 establishes a pattern. 3 begins to define a trend. We're still in the early stages. We've confirmed 3 interstellar objects. We need dozens more to draw meaningful conclusions. But the universe doesn't provide samples on demand. Objects like 3I Atlas are rare in human timescales. The galaxy is enormous. The odds of another interstellar comet passing this close within the next decade are uncertain. We might wait years for the next detection, or we might find one tomorrow. The randomness is frustrating for scientists who prefer predictable experimental schedules. Meanwhile, questions accumulate. Why did this comet stay active so long? How did it retain volatiles through millions of years in interstellar space? What does its chemical signature reveal about star formation in other regions of the galaxy? Are we witnessing a common type of object, or is 3I Atlas unusual even by interstellar standards? The answers will come slowly. Data analysis takes time. Peer review ensures accuracy. Model refinement requires iteration. This is how science works. Carefully, methodically, building confidence through repeated verification. But while the scientific process moves deliberately, the human imagination runs ahead. We wonder what it would be like to follow 3I Atlas back to its origin, to trace its path backward through space and time, past stars and nebulae, until we reach the molecular cloud where it formed, to see the system it came from, to know whether planets orbit that distant star, to understand whether life emerged there, or could emerge, or already did and died long ago. These thoughts are unprovable, but they're also unavoidable, because 3I Atlas represents more than data. It represents connection, a physical link between our corner of the galaxy and somewhere else. A messenger that crossed the void and arrived here, carrying information we're only beginning to decode. And when it leaves, when it fades back into the darkness, it will carry something with it. The knowledge that for a brief moment in cosmic time, it passed close enough to a small blue planet for the inhabitants to notice, to photograph, to study, and to wonder. We cannot follow. We cannot retrieve it. We can only watch as it departs, knowing that it will continue traveling long after our civilization has ended, moving through the galaxy on a trajectory that might eventually bring it near another star system, where perhaps other observers will detect it and ask the same questions we're asking now. The universe is full of these connections, objects that move between systems, information that migrates, matter that cycles through stars and planets and the spaces between. We're part of this network, whether we realize it or not. Observers embedded in a cosmos that is constantly exchanging material and energy across distances we find almost incomprehensible. 3I Atlas is a reminder that we're not isolated, that our solar system is not sealed off from the rest of the galaxy, that visitors arrive rare and unexpected, carrying stories we can partially read if we have the tools and the willingness to look closely. The images will remain. The data will be archived. The papers will be published. And someday, when another interstellar object appears, researchers will compare it to 3I Atlas, using these observations as a baseline to measure how similar or different the new visitor is. That's how knowledge builds, slowly, one observation at a time. Each example adding to our understanding, expanding the range of what we consider normal, pushing back the boundaries of what we know how to explain. 3I Atlas won't be the last, but it might be the most thoroughly documented interstellar comet we study for a generation. The clarity of these images, the diversity of instruments used, the extended observation period. All of these factors combine to make this object uniquely valuable for science and uniquely memorable for everyone who watched it pass through. So tell me, what do you think happens next?